Okay, so part 3 of this section 2D notes. On the back of your graphics page that had the 2 charts on it, you have at the top a changing the state of water graph title. And you have a diagram at the top, and then you have at the bottom a graph that we are going to do. So that's the page that we are working on. And I understand that there's a glare on this. I'm going to take a picture when I'm done so that you have it. I'm at the carry out, so I can use the whiteboard, and this is the only place that I can set my camera up and whatever, okay? So I understand it's not the best, but I promise I'll get you a picture of it so that you can see better. So I had to make it smaller because my whiteboard is not very wide. But we have a solid here, a liquid, and a gas. So what I would like you to do is write in there the state of matter that it changed, the process is called when it changes from, for example, a solid to a liquid. So if it goes from a solid to a liquid, it is called melting. Obviously, you will have more room to write this, and I thought it would be very neat. From a liquid to a gas, well, let's do this one. Well, liquid to a gas is called vaporization. Okay, I'm going to run out of room there. And then from a solid directly to a gas, it's called sublimation. All right. Going the other way, when we go from a gas to a liquid, it's called condensation. When we go from a liquid to a solid, it's called freezing. And when we go from a gas directly to a solid, it's called deposition. Okay? So what I want you to see is that we have pairs again: melting and freezing, vaporization, condensation, deposition, and sublimation. And on the back of that page, or the front of the page that we're working on right now, in those 2 charts, you should see those patterns with endothermic and exothermic reactions, with absorb and release energy. You see a pattern. Okay, so I just want you to see that every arrow that goes this way is an endothermic reaction. Solid to a liquid, liquid to a gas. The molecules have to move faster, and so they take in energy so that they can move faster. They're going to have to absorb energy. Every arrow that goes this way, condensation, freezing, and deposition, is going to be exothermic. And they are going to release energy because they need to get rid of it so that they can start moving slower and slower and slower. Okay? So for some of you, that's no new information, but that visual will help some of your brains make those connections. Okay? Now I'm going to take these. We're going to move around to the other side. And you have a graph there. Okay? Now the directions say, create a graph showing the changes in the state of water. Include ice, liquid water, steam, the melting point, and the boiling point. The x-axis should be time, and the y-axis should be temperature in degrees Celsius. Add any other pertinent information or information that you think is important. So, we are not going to add numbers. Well, let's do what it asks us to do first, okay? Temperature goes on this, on the y-axis. So here we have temperature, and we have it in degrees Celsius. Here we have time, and it could also be labeled as energy. And for both of these, it increases this way as you go up the y-axis or to the right on the x-axis, just like a normal graph, okay? Every change of state graph looks exactly the same. Doesn't matter what the substance is, the material is. So here's what it looks like. You have 3 slants and 2 plateaus in every single one of them, okay? We are going to use water as an example because the 3 states of water we are familiar with from everyday life. They happen in a fairly short range of temperatures, so we're familiar with them. But it doesn't matter what the material. The graph will always look like this. All right? So here's how I remember it. Here is the Birchism. There are 3 states of matter. And on this graph, there are 3 slants. Okay? So here is your solid. It is going to be the one that has the less amount of energy, and it's going to be at the lowest temperature. So solid goes first. The next one will be liquid, and the next one will be a gas. So for water, this is going to be ice. This is going to be liquid water, which is kind of a weird way to put it. And this is going to be steam. Okay? But we could be talking about mercury, we could be talking about iron, we could be talking about copper, hydrogen, whatever it is. Okay, they all can be in a solid state, they can all be in a liquid state, and they can all be in a gas state. That's why we're not putting numbers here, because that will change for the substances. But the shape of the graph will never change. Okay? So, as we are moving, let me get another, try to find another color here. As we are moving this way to the right on our graph, do you see that as we start here, that we are increasing in temperature and we're also increasing the amount of energy until we get to this point. Then, as we go to this point, the temperature doesn't change, but the amount of energy into the system does. Okay? The temperature doesn't change, but more and more and more energy is being added into the system. So then we turn into a liquid. At this point, and again, energy is inputted into the system and the temperature rises. But at this point again, to this point, the energy increases, but the temperature doesn't change. Energy just keeps getting added into the system. The temperature does not change. And then at some point, those molecules turn into a gas and go on. Okay? So here's the question. Usually I have you guys do this, but since I'm here by myself, I guess I will have to tell you. I want you to label these points as melting point, boiling point, freezing point, and condensation point. Okay? And it should be fairly simple. If you're going this way, when does it go from a solid to a liquid? That's when it's going to start to melt. So that is the melting point. This, maybe I should have. This is going to be then the opposite of that, or the freezing. Okay, let's not do that yet. All right, let's just keep going in one direction. And then here, when it starts to go from a liquid to a gas, that is going to be the vaporization point. And actually, we call that the boiling point. Okay? So let's just use BP because that's what it is used in science. Okay, that's the boiling point. Now, as we move back this way, this is going to be the point where the gas starts turning into a liquid. So that is its condensation point. And here is the point where it starts going from a liquid to a solid. So that's its freezing point. You need to know those. For whatever reason, the state says that you need to be able to read one of these and you need to be able to create one of these. Now, I don't want you to do this. Okay, I don't want you to do this. But just for an example, do you see here, what's the melting point of water? Or the freezing point of water. It's either going to be, well, it's here. It's either going to be 0 degrees Celsius or 32 degrees Fahrenheit. Okay? So here it's 0 degrees Celsius, here it's 0 degrees Celsius, here it's 0 degrees Celsius. The temperature doesn't change, but the amount of energy going into the system does. Same thing up here. If we did this for water, it would be 100 degrees Celsius or 212 Fahrenheit. We have ours in Celsius here, so this would be 100. Here's the million-dollar question. What state of matter do we have right here? If here we have a solid and here we have a liquid, what do we have on the plateaus? So in between a solid and a liquid, what do we have? Okay? We are going to have ice and water. The closer we are to this point, the more ice there will be. The closer we are to this point, the more water there will be. So it's a continuum of ice and water. Up here, along this, what do we have? Well, we have liquid water and we have steam. Again, the closer we are to the boiling point, the more liquid there is. The closer we are over here, the more gas there will be. Steam, in this case, if we're using water as an example. Okay, so for whatever reason, like I said, I don't quite understand why, but the state says that they think it's important that you know this. So, we have that for water. Understand that it's the same for any material that we may have, any substance. They can all be in a solid state, a liquid state, or a gas state. The thing that changes is the temperature at which those things happen. And remember, temperature is nothing more than a measure of how fast the molecules are moving. So if they're just vibrating in place, they're going to be a solid. If they're sliding past each other, they're going to be a liquid. If they're bouncing off the walls of their container and each other, then they're going to be a gas. Okay? I think that will do it for the states of matter lectures.